if I have a zero thickness airplane, no angle of attack, right? No airplane at all. Rho u is finite, right? That just flows, the air just flows through. D square u dx square is 0, and this is also 0. This is also 0, right? There are no derivatives. Now, when I take an existing flow field where these derivatives are non-zero and shrink it by a factor of 2, rho u stays the same order of magnitude, right? Doesn't change much. The derivative of u with respect to x squared decreases by how much? If I shrink the amount of perturbation by a factor of 2, 4? Are you sure? I'm not enlarging the airplane by a factor of 2. I'm just decreasing the perturbation to velocity by a factor of 2. So I mean, if you want to make it clearer, right? So u is equal to u infinity, which is constant, plus a, let's say, delta u. What I'm asking is, okay, so rho is the same, is equal to rho infinity plus delta rho. What I'm asking is, if I shrink both deltas by a factor of 2, okay, how much does that term shrink? By a factor of 2, right? I mean, the derivative is a linear operator, which means if I scale the field by a factor of 2, the derivative scales by a factor of 2. But how about this term? It shrinks by a factor of 4, right? Because this term shrinks by a factor of 4, this term also shrinks by a factor of 4. So essentially what I'm saying is that in the limit of small perturbation, as you make the perturbation smaller and smaller, this term becomes more and more negligible compared to this term. Right? So all of the equation I'm deriving is at the limit of when the perturbation caused by the airplane is very small. And that's the only way you can derive a set of linear equations. Right? As we have looked at the shock equations, and you see a lot of nonlinearity. Right? So if you increase the Mach number by a little bit, you don't see the downstream Mach number decrease proportionally. You have this. If you look at the normal shock curves, they're all nonlinear. I mean, the shock is one of the most nonlinear phenomena. And the only way you can derive a set of linear equations is by assuming all the shock waves are infinitesimally weak, right? So basically, the perturbation due to the airplane is very small, and all the shock waves, all the oblique shocks are very, very weak. Okay, is that clear to everybody, like how we derived this equation? I mean, all the other things are the same, right? When you're taking derivative of this to y, you're also taking this derivative with respect to y, and this multiplied by this, it's second order, like it's what we call a second order small quantity, okay? Same thing when you do the derivation here, right? So you divide the rho to here, you get u over rho c squared. The derivative of this multiplied with the derivative of p also decreases. It's also a second order quantity. All right, so that gets neglected when we think about this perturbation to p, and the u and v and w are small. All right. Okay, so today we'll spend the entire lecture explaining the significance of this equation, especially on supersonic flows. At subsonic flows, this equation is known in mathematics as an elliptic type partial differential equation. Okay, you have second order derivatives, and the sign of all the second order derivatives are all of the same sign. But while Mach number exceeds 1, one of these derivatives suddenly switch sign. In mathematics, the property of the partial differential equation changes suddenly. It's now called a hyperbolic partial differential equation. And in the middle, you have parabolic. That's when this second derivative vanish and you have a first derivative somewhere, right? So in aerodynamics, the parabolic doesn't occur when you neglect viscosity. So essentially, when all these are the same sign, you have hyperbolic PDE, and when these switches sign, you have a parabolic PDE. And these are not just the names. It reflects in the solution very prominently when you have a subsonic or elliptic PDE. Any perturbation, think about you change the geometry of the airplane, right? That's a perturbation to the differential equation. The solution responds to the perturbation in an infinite way, in the sense that the entire flow field would change, albeit slightly when the flow field is very far away from the perturbation, right? But think about our solution to the Laplace equation, right? We have the source and sink and the vortex. When you add a vortex or add a source or add a sink, you see the entire flow field actually change, right? The change actually decreases as you move away from the source or sink or vortex, but actually the entire flow field does change. And this is, the behavior is the same as long as Mach number is less than 1, you have the elliptic type. While when m exceeds 1, you have a hyperbolic partial differential equation, and the response to a perturbation suddenly would change. The solution would no longer respond to a perturbation in an infinite way, in the sense that there is a lot of regions where the perturbation would no longer affect. That's where we have supersonic flow. For example, when the front of the airplane would not even sense the presence of the airplane, right? That's reflected in this hyperbolic PDE. And today we'll be looking at we are going to go from very simple scenarios and give you some intuitive sense of how the solution behaves.